Hello and welcome to the discussion series of production technology theory and practice course. So, let me remind you that in our last session we started discussing the tool life and the effect of various parameters, various variables on the tool life. So, we said that on tool life there are basically there are 5 variables which affect the tool life. First is the cutting parameters, that includes the cutting parameters like cutting speed, feed and the depth of cut particularly. Then there are tool angles, particularly the rake angle, flank angle and the cutting edge angle. Then the tool materials, workpiece materials and the cutting fluid. So, these are the 5 basic variables, those are used in the case of the machining. They actually all of them affect the tool life in a different way. So, we discussed that the cutting speed has the greatest effect, that has been already found out from the experiments, from the research, and the first initiative was taken by the F.W. Taylor, who has invented the Taylor's tool life equation, which is famously given as the V, that is the cutting speed tool life to the power constant n is equal to some constant. Okay. So, then we said that in this Taylor's tool life equation that Taylor could consider only the cutting speed, okay, because V t to the power n is equal to c, you can see that only the cutting velocity is there in that equation, all right. However, the further experiments, further research shows that not only the cutting velocity, but the feed and the depth of cut will also have the effect on the tool life, and it has been seen that the cutting speed has the greatest effect on the tool life, followed by the feed and the depth of cut, that we have discussed. Next that we started discussing is the effect of the cutting tool geometry, and in that case when the cutting tool geometry is concerned, then the rake angle has a great effect on the tool life, because overall, as we have seen earlier also, that as the rake angle is increased, the cutting force decreases, all right. And if the cutting force decreases, then the temperature will be decreased, and as the temperature is decreasing, the thermal effect, thermal deformation of the cutting tool and the thermal softening of the cutting tool will be less. So, the tool wear will be less and the tool life will increase. So, this is an overall conclusion, that overall if we increase the rake angle, then the tool life will be increased. Okay. But here what we have seen then, and that we have shown, that if the cutting tool angle, rake angle, if we increase infinitely, then after a certain value, when we get the maximum tool life, after that the tool life decreases with the further increase in the rake angle. This is because as we further increase the rake angle, the cutting angle of the tool decreases. That means the tool becomes weaker, tool becomes less strengthy, that is the strength of the tool becomes less, and the less material is available for the heat conduction. So, the tool becomes mechanically weak, that means it can actually break, okay, and also it can be thermally affected, because the heat is accumulated, and the heat, because of the cutting process that is increasing, that cannot be conducted from the tool, and therefore, the tool wear will be more and the tool life will be less. So, after that, after further increase in the rake angle, the tool life will be decreased. So, these are the things that we have discussed. Also, we said that if the tool material or the workpiece material particularly, we said if the workpiece material has more strength, this optimum value of the rake angle should be low, okay, Low because the tool has to be fatter, of course. The strength of the tool has to be more for removing the material from the workpiece which has more strength. And then we said about the flank angle the same thing, that as the flank angle increases, the rubbing between the flank face and the already machined surface will be less. So, therefore, the temperature occurring will be less in the zone, in the cutting zone, and the thermal deformation of the tool will be less. Okay. But again, if we further increase the flank angle after we obtain the maximum tool life, then the tool cutting angle will be again less, tool will be weaker, and the less material will be available for the heat conduction. Then again the tool life decreases. So, therefore, we have a maximum tool life for a certain value of the flank angle as well as the rake angle, which we are calling as the optimum rake angle or optimum flank angle. Now, in case of flank angle, if the feed is more, then we have seen that the optimum angle that we are obtaining for the maximum tool life, that has to be less, because for more feed we need to have again the strength of the tool more, and we have to have the more material for the heat conduction from the tool. So, these are the things that we have discussed. As you can see from here, these are the variables, 5 variables which affect the tool life, and the temperature occurring during the process, during the machining process is proportional to root over Vc, that has been said. Okay. Then we said that increasing the rake angle reduces, this is the one that I have shown it to you, all right. And then the final conclusion, we said that the higher is the strength of workpiece material, lower is the value of the optimum rake angle, which I said just now. About the flank angle, I have shown it to you that as the flank angle is increasing, then the cutting angle of the tool, which is this, okay, this is decreasing, and the tool becomes weaker, and the material available for the heat conduction will be less. Okay. So, also we said that the optimum value that we are getting for flank angle, this also affects the feed rates, okay, affected by the feed rates. That means, higher is the feed rate, lower is the optimum value. The flank angle therefore should be low if higher feed values are to be used. So, in case of rake angle, we said that is the hardness or the strength of the workpiece material, and in this case for the flank angle we are saying that if the feed is more, then our optimum value of the flank angle should be lower. Okay. So, these are shown in the curves here. So, if you see here that the sigma 1 is more than the sigma 2 than the sigma 3. So, here also this is in the increasing order. Okay. So, sigma 1 is maximum. In that case, the optimum value that we have to get, we will get for the rake angle will be less than the other values of the strength of workpiece material. Similarly, here also this is in the increasing order, that means F1 is more than F2 than more than F3. In this case, this optimum value that we are getting for the maximum tool life, that has to be less than in case of the other values for the other feed rates, which are less than the one that we have discussed here. Okay. So, this much we have discussed. Now, the next that is the tool and the work material. Okay. Now, overall the research has says that the tool material must be at least 35% to 58% harder than the work material. All right. This conclusion has been made by the research by Professor Loladze. Okay. And Loladze is a Russian scientist. He has actually shown that the tool material must be at least 35% to 58% harder than the work material. Okay. Now, the high strain rate of deformation and elevated temperature of the work material further complicate the situation. So, there are two things that happen during the machining process. All right. The strain rate of deformation is very high, high strain rate of deformation. Then only you can have the plastic deformation and segregate the workpiece material from the excess workpiece material from the blank, all right, as well as there is a very high elevated temperature. So, these two phenomena, that is high strain rate of deformation and the elevated temperature, this affect in the following way. With the increase in machining speed, the temperature of both the tool and the work material increases. That have been discussed many times earlier, that as we are increasing the speed, the temperature increases, and that I have already shown you through the curve also, that the temperature is proportional to root over Vc, okay, that is the cutting velocity. This results in a lowered effective hardness of the tool, because the temperature increases mean the tool is thermally becoming softer, okay, through tool thermal deformation of the tool happens and the tool material becomes soft, all right. Unfortunately, the expected fall in the hardness of the work material is neutralized by the higher rate of deformation. Let me explain this to you. What does it mean? The tool and the workpiece, they are in contact with each other, okay. Now, we are saying that in this process, when the material is removed because of the interaction between the tool and the workpiece, two things are happening. One is the very high strain rate of deformation given by the force which we are imparting on the workpiece through the tool, and second thing is that when particularly the speed is very high, the temperature is occurring, high temperature is occurring, okay. Now, because of the high temperature which is occurring, the tool is getting thermally softened. Actually, the same temperature should have gone to the workpiece as well, and the workpiece as well should have been thermally deformed, but what is said is that tool is becoming thermally deformed, okay, thermally softened, but workpiece does not, because the high strain rate of deformation is imparted on the workpiece, okay. And as you understand that the high strain rate of deformation means the resistance will also be higher, okay. So, then the strain hardening takes place in the workpiece material, and the workpiece material as if has been given an added hardness, okay, because of the high strain rate of deformation, and therefore, that elevated temperature which was supposed to soften the workpiece material does not do that, because that is compensated by the strain hardening process, by the extra hardness which is imparted on the workpiece because of the high strain rate of deformation, because high strain rate of deformation is imparted to the workpiece, not to the tool, all right. The tool is imparting the high strain rate of deformation to the workpiece. So, the added hardness is or the hardness is additional hardness is added to the workpiece material. This is what happens, and because of that the hardness of the tool has to be more than the workpiece material because of this phenomena. Once again, because of the high strain rate of deformation and because of the elevated temperature, okay. In general, harder the work material, higher will be the tool wear rate and lower will be the tool life. This is obvious, as the temperature is increasing, then the tool is getting thermally softened and the tool wear is faster, is more, and the tool life is less, tool life decreases. So, this is the entire thing that can be concluded that as the temperature becomes more, so tool life getting less. For cutting fluid, cutting fluids are primarily used for decreasing the cutting temperature, I told you that, okay, and the chip tool interface friction. So, there are two actions of the cutting fluid. One, that is when the cutting fluid is applied, basically the temperature which is occurring in the machining zone, part of it can be taken away. Why I said part of it? Because part of it goes by the chip, because the chip is segregated, chip goes away, and chip takes away most of the heat, a large portion of the heat, but still the heat remains, a lot of heat remains in the machining zone, and that can be removed, that should be removed, because otherwise the tool life will be less, that we have seen, and that is done by the cutting fluid. Another action of the cutting fluid is that cutting fluid reduces the friction between the tool and the workpiece, particularly between the chip and the tool in the rake face, okay, because as it is moving along the rake face of the tool, if the friction between the chip and the rake face of the tool is more, then the more temperature will be produced. So, if we can reduce the friction, in that case the temperature also occurring will be less. They also serve to keep the workpiece cool, of course, to avoid the thermal expansion, provide a rust proof layer. Rust proof layer is provided because to the cutting fluid there are different kind of additives. Okay. Those additives, they actually put a layer on the freshly removed workpiece surface. All right. Now, when the workpiece surface is freshly removed, it is prone to the oxygen of the atmosphere, and it can get oxidized. All right, and the rusting can happen actually. So, this is, as you understand, the rusting is bad effect on the surface of the workpiece. It can spoil the workpiece, it can spoil the surface finish and so on. So, that actually gives a coating so that the rusting does not happen on the nascent surface of the workpiece immediately after the fresh layer is removed from the workpiece, and remove the chips from the machining area. So, this is another problem which many times are faced, and I have already discussed this, that removal of chip can be a problem. Otherwise, if the particularly when the ductile material is machined, then the continuous chip will be formed. Okay. And if the chip is not removed from the machining zone, in that case the chip can get entangled with the workpiece, chip can get entangled with the tool, it will rub the already machined surface, it will rub the tool faces, rake face and the flank face, and it can spoil the geometry. Okay. Now, we said about the chip breakers. There are chip breakers which have to be used particularly when the ductile material is machined, because those chips, continuous chips, have to be removed. Okay, but apart from that, the chips can also be removed particularly when they are small chips from the work zone, okay, machining zone, by high speed high speed flow of the cutting fluid. This is also another action of the cutting fluid. Cutting fluids should have high specific heat, so that most of the heat can be large amount of heat can be conducted from the machining zone, and good thermal conductivity, okay, so that the heat is conducted away. A chemical constituent to form weak junctions should have a low viscosity and small molecular size, non-corrosive and inexpensive. Let me explain it to you that why they should have a chemical constituent to form the weaker junction. There are two reasons. Okay. Weaker junction means that the chip which is being formed with a freshly removed surface, it should not have the tendency to get welded to the rake face of the tool or to the tool tip. And if you remember, we said that that causes the built up edge formation. Okay. So, if there is a layer on this, if there is a coating made by the cutting fluid, in that case the built up edge formation can be prevented to a large extent, even if the speed range is that in which the built up edge normally is formed. I will remind you that in case of mild steel and high speed steel as the tool and the mild steel as the workpiece, in that combination of materials, that cutting speed is about 80 to 110 meter per minute. Okay. So, within that range of the speed, cutting speed, the temperature is such that the built up edge forms. All right. Now, when the built up edge is formed, then of course they are getting welded. So, they will get welded only when the two surfaces are nascent surface, okay, because a very thin layer of chip is removed from the chip, a very thin layer of the material is removed from the chip surface as well as from the rake face of the tool. So, they get welded because they are nascent and they will have the affinity to each other. So, if it is coated, both the surfaces are coated, the rake face and the thing, but that coating will be by the cutting fluid, and the cutting fluid for that reason should have some chemical constituent so that the coating can be made. And another purpose I just now explained it to you, that is to resist the corrosion. Okay. So, it will not be corroded. and then it should have the low viscosity and small molecular size, so that the cutting fluid can penetrate easily to the machining zone, because cutting process happens at a high speed. So, there should be enough time for the cutting fluid to react to the surfaces which are being machined, or the freshly removed surface of the workpiece. Okay. So, therefore, they should have the cutting fluid should have the low viscosity, so that it can flow easily and flow to the up to the tool tip, because at the tool tip the temperature is maximum. So, the cutting fluid should reach there, so that it could be cooled down, all right. And small molecular size for the same matter, for the same reason. It should be non-corrosive and inexpensive. The cutting fluid itself should not corrode the workpiece, and of course, it is easily available, because as you know that the cutting fluid is flown to the working zone in a very large quantity. Okay. At a very high speed, the coolant is ineffective. Coolant is ineffective because at a high speed there is no time for the coolant to reach to the zone, machining zone. And if you see, probably it is not given here, if you see that, suppose we have, if we draw the curve between, let us say okay, and mu. So, here is the cutting velocity, let us say. So, here what happens is, what I mean to say is, let us not come into that, because this will be too big a discussion. Overall, what I am saying is that at very high speed, the mu cannot be reduced to that extent what is desired for the from what is desired from the coolant. Okay. Similarly, the cutting force cannot be reduced to that extent when it is this thing. Okay. Overall, what I said is, let me finish then this, that if it is for example, mu, coefficient of friction, and let us say this is the force, all right. So, if it is dry cutting and this is the cutting velocity, okay. If it is wet cutting and this is the dry, this is also, let us say, dry, and this is wet. Okay. Here are the curves in one word. We are not going into more details of this discussion. So, through this I wanted to show you that when the cutting fluid is used, overall the force is reduced. Okay. You can see that from here, that in the dry cutting the force is here for a certain value of the cutting speed Vc1, and as it is increasing, it is going like this, and at a higher speed, if you see this, the dry cutting value and the wet cutting value, they are becoming very close. So is the mu. So, as I said, overall that the mu cannot be reduced to that extent at a higher speed. This is the experimental result, that at higher cutting speed, the wet cutting and the dry cutting, this is the wet cutting and this is for the dry cutting. Okay. They are basically almost close to each other, all right, and they does not get any, I mean there is no effect almost. It is only because that there is no time for this to get it. Another reason why this happens, like suppose if we say that this is the machining zone, this is the machining zone, this is the tool, okay. This is the workpiece. Now, here we are supplying the fluid, okay, cutting fluid. So, what happens is that at a high speed, the coolant will come at a higher speed here through this, and here there is a wedge, all right. This wedge will not allow the coolant to come to the tool point at this edge, okay, or the cutting tool point where the temperature is maximum, all right. This is because there is a hydrodynamic force, and that hydrodynamic force happens when it is in wedge shaped. This is the wedge, and here also there is a wedge, and the fluid is being passed at a high speed. So, these are the two reasons, that this is because of the hydrodynamic force which is created in the wedge between the tool and the between the flank face and the already machined surface, and between the rake face and the chip. Okay. Here these are the two places. Also, because of the very high speed, the time is insufficient for the coolant to reach the tool point and cool down the workpiece. Okay. Now, if you see, let us discuss some of the applications through some of the problems, okay, numerical problems, how we can implement the one or the tool life equation, the tool life theory that we have learned in life. Let us say tool life test in turning yield the following data. Cutting speed is 100 meter per minute when the tool life has shown to be 10 minute, and as the cutting speed decreases to 75 meter per minute, the tool life increases to 30 meter minute. From this data, we have to determine the constants n and c values of the Taylor's tool life equation. Okay. Based on your equation, compute the tool life for a speed of 90 meter per minute. So, if the tool life is in between, what should be the speed, what should be the tool life, and the speed corresponding to a tool life of 20 minute. Okay. So, 20 minute will be in between the 10 minute and the 30 minute, and find out what should be the speed here. Now, how to solve it? Like two equations we have, V t to the power n is equal to c, V t to the power n is equal to c, n and c unknown for the first in a tool or the first machining. For the second machining process, we have the V t to the power n is equal to c. So, we have two equations and two unknown n and c. So, n and c could be found out if we simultaneously solve these two equations. Okay. Here is the equation, these two equations, how they are simultaneously being solved. This is shown here. Okay. So, n we can find out as 0.2619. Put in one of these equations the value of the n, you can find out what is the c. So, the constants have been found out. In that case, the second problem, that is the tool life for a speed of 90 meter per minute, that can be easily found out, because in that case the tool life is not known, V is known, V t to the power n is found out is equal to c. So, it is one equation and one unknown, which is t, it can be solved and found out. The t is equal to tool life is 15.13, you can solve that. Now, the third problem was that the speed corresponding to a tool life of 20 minute. Here the t is given, but the v is not given. Again, this is the same procedure, that V t to the power n is equal to c, except v, all other parameters are known. So, you can solve it and find out the value of the speed when the tool life will be 20 minute. So, you can see that the implementation is easy when you know the concept, when you know that what is the tool life, how it actually varies with respect to cutting velocity, then you can find out, you can implement them to solve any problem. Let us say another problem will be the turning tests have resulted in 1 minute tool life for cutting speed of this and 20 minute at a speed of this. Find the n and c values. So, probably these two are similar, that for data 1 t is given, then c is this, here the c is given. So, c have to be taken in meter per minute, it is given as meter per second. So, you have to take it as meter per minute, and for data 2 also v is given. So, v has to be taken in meter per minute. Okay. So, you can find out what is the value of n from here using again the Taylor's tool life equation. Okay. And from here the constant n can be found out, and here in the B project how long the tool would last at speed of 1 meter per second. 1 meter per second is 60 meter per minute. T has to be found out, one equation, t is unknown, you can find out the t. All right. So, similarly, in a production turning operation, the work part is 125 millimeter in diameter and 300 millimeter long. So, here physical parameters are given, that is what is the diameter of the workpiece, what is the length of the workpiece. Okay. Then the feed rate is given as 0.225 millimeter per revolution for the operation. If the cutting speed is 3 meter per second, the tool must be changed every 5 work parts. but if cutting speed is 2 meter per second, the tool can be used to produce 25 pieces between the tool changes. So, you have to understand that how the tool life can be measured or tool life can be calculated from this data. Here, look here, this is different from the other problems, like here what is given is that cutting speed is given, the tool must be changed for 5 work parts. So, the life is not given, but 5 work parts can be machined, all right, and so on. Determine the Taylor's tool life equation for this job, that is N and C have to be found out. Now, the T, this is the tool life, this is given by pi d n, okay, by this. So, you can find out easily what is the T m, that is the machining time, okay. Machining time is this. So, the tool life, that is 5 work parts, you can you have to change the tool after each 5 work parts. So, 5 into this machining time will be this 14.54 minute, which is the tool life. So, you find out the machining time, okay, and machining time I have already discussed it with you, you remember, that is the L by Fn, isn't it. So, that is what we are doing here, and from here you can the number of passes, let us say 1, we are taking as into n, but n is the number of passes, this we have taken as 1. So, this is L, and here pi d n is taken because n is taken as the Vc, pi d n, and n is equal to Vc by pi d, right. So, therefore, the T m can be taken as pi d L divided by F and the Vc, okay. We have put this value of the n in here, and this will be pi d L divided by Vc and the F. So, this is shown here, this is the one. From here you can find out what is the time taken for machining, that is the machining time. Then the machining time is this. So, 5 parts can be machined, all right. So, that you can, after which you have to change the tool. So, that takes the tool life as 14.54 minute. So, that solves the first part. Then you have the second condition, okay, and from the second condition, the similar way you find out the machining time, and then tool must be changed 25 after 25 pieces. So, 25 into this time is the tool life, and then you have this equation, okay. So, in one case it is 3 meter per second, which is this, and in second case it is this. So, you can find out what is the V t to the power n is equal to c in first case, in the second case V t to the power n is equal to c. In both cases V and t are different, we found out from here, from these conditions, okay, that if the cutting speed is 3, then tool must be changed after 5 work parts, and the second equation is if cutting speed is 2 meter per second, then the tool must be producing 25 pieces. From here we can get these 2 equations, okay, and 2 equations, 2 unknown n and c, you can solve like we have seen it earlier, and we can find out the value of the n and the value of the c. So, therefore, the tool life equation has been asked. So, V t to the power 0.2012 is equal to 308.43. Okay. So, this is the tool life equation, this is the answer. So, you can see that these are also not so difficult, and by understanding the problem, by understanding the first of all you have to understand what is asked here, all right, and then you have to scrupulously apply the theory that you have learned, that is the tool life equation, and from the tool life equation you can actually solve the problem. Okay, so now here if you see this in this slide, here is a complete pictorial view of a lathe machine. In the lathe machine that we will see in the lab also in details how these machines work. Here is the headstock, all right. In the headstock we have the basically the gear train, okay, and the gear train provides the rotation to the spindle, and the spindle, on the spindle there is a chuck to mount the workpiece, So, the chuck can be 3 jaw chuck or it can be 4 jaw chuck, that we will explain in details later in the lab. Apart from that, there is a tailstock, and this tailstock assembly has the tailstock quill, okay, and in the quill we have the dead center. So, the dead center means the center does not rotate, as many of you might be knowing that, and there is a live center where the where it rotates. This is the handle by which this quill can be forwarded. So, apart from the headstock and the tailstock, we have the tool post. In the tool post also we have the apron here. So, this apron moves on the lead screw, this is the lead screw, all right, and through this also the feed rod goes in, which supports the apron when the feed is given, all right. Now, here if you see that these are the selector for the speed. By selecting this or by rotating that, you can have a particular combination of the gears in mesh, so that you can have a different kind of transmission ratio and the different RPM given to the spindle of the machine. This is the feed box. So, inside the feed box we have the feed selector, okay, what kind of feed we are willing to supply, and this is the clutch. So, when this clutch is on, so then the feed is given, okay, feed is on. This is another clutch for the feed. So, this we have seen. Now, this is the longitudinal and the transverse feed control, these are made by here. So, these are the handles, either you rotate this so that you can have the apron moving along with the tool post towards the headstock or towards the tailstock, and by rotating this you can actually give a cross feed. Cross feed is given as you understand that this is for the facing operation, all right. So, this is the cross slide for that, okay. And on the lathe bed, all right, we have the these are the ways, guide ways on which the apron, the tool post moves on the lead screw. So, this is the lathe bed, all right. So, this is overall many of you must be familiar with, this is the lathe machine, and these are the details of the lathe machine. And here are the different kind of surfaces that can be made in the lathe machine, using the lathe machine. I told you about the cross feed. So, this is the cross feed that is given here along this, all right, and particularly here what is given here is the tool, okay. Look at the tool, how the tool can be moved along the direction which is perpendicular to the axis of the workpiece, okay. If the feed is given initially, if you remember, I told you that if the feed is given not parallel to the workpiece axis, then a taper surface is formed. So, the feed is given, you see, at an angle inclined to the axis of the workpiece. Axis of the workpiece will be here, okay. And if it is a cylindrical job, then the 3 jaw chuck is used, so that 3 jaw chuck can self center this this kind of a cylindrical workpiece. Here is a contour turning, and in contour turning accordingly the feed will be given. The feed is neither straight nor inclined, it will be along this curve which will be predetermined, and the feed is given like this. This particularly you can see very well how this is given in case of CNC machine. There we will show you how this feed is given for the contour machining, for the contour turning, and how this can be programmed, so that automatically the tool moves along a contour of the workpiece and the entire surface is made. This is the form tool. Form tool has a form and which is conformed to the workpiece to make the form, okay, this kind of a curvature. This is chamfering. The chamfer is made, you know, for the guidance, so that this could go well in the hole, all right. This is the cutoff, that means again the feed is given, the cross feed is given similar to the facing, so that the two parts are separated, okay, and this feed is given towards the axis perpendicular to the axis of the workpiece. This is threading. Threading we will show you in details in the lab, okay, how the feed can be given for the threading and how this threading can be finished, particularly in different passes, and in different passes when the tool comes back to the initial position, it can actually go, it should go along the same path, otherwise the thread will not be properly machined, of course. This is boring. This is done for getting the internal hole, and the internal hole to enlarge the diameter, particularly to enlarge the diameter of the internal hole. So, this diameter of the internal hole was existing, let us say it was obtained by drilling, okay, and this can be enlarged to this diameter by a tool which is called the boring tool, and this also can be done by in the turning lathe. So, all these operations are performed on the turning lathe that we have already seen here. Okay. So, drilling also can be done. In case of boring and drilling in the turning, boring tool and the drill are fixed here, okay, at the tailstock, and they do not rotate. That is the difference between the drilling machine and the drilling of a hole in the turning. So, in that case the job will be rotated, job will be fixed here, and in the tailstock the tool is the drill or the boring tool. The boring tool is, of course, boring tool is fixed in the tool post, and the drill is fixed in the tailstock. Okay. So, hole can be drilled and that hole can be enlarged by the boring tool. Okay. Knurling can be made. So, this is the knurled surface. Knurling can be made by a special tool which is called the knurling tool, and this also will show you in the lab in more details. So, you can see that with the help of different kind of relative movements between the tool and the workpiece, different kind of surfaces are formed. Okay. So, in each of them the relative movement between the tool and the workpiece is different. So, to form the facing operation, make the facing operation, to form the taper surface, contour surface, formed surface, and so on. Okay. Here you can see the methods of holding the workpiece in a lathe. Right. Here this is the holding between the centers. This also we will demonstrate you later. This is the center in the tailstock, and this is the other side which is held on the another center on the headstock, and the rotation is given by a dog carrier. Okay. Here is the dog plate, and this is called the dog and the dog carrier. This is the carrier dog plate which is fixed here with the workpiece, and the rotation is given from the chuck. As the chuck rotates, this is inserted in that groove, and therefore, this dog plate will rotate along with the workpiece because it is fixed here, and this is supported by the center, okay, and the other center, as I said, at the headstock side. This is the chuck, and this chuck, if it is 3-jaw chuck, so this is the self-centered. There could be a 4-jaw chuck also, and the 4-jaw chuck is not self-centered, where the cylindrical jobs are not mounted, not clamped, but for the 3-jaw chuck, since it is a self-centered, so center of the workpiece has to be exactly coaxial with the center of the spindle. Okay. So, for that purpose the 3-jaw chuck, which is adjustable to clamp the work, is used. This is the collet chuck, and the collet chuck with the 3 slits to permit the squeezing of the work. So, I told you once, and we will show it in the lab as well, that this workpiece can be inserted here, and that whole collet goes into the spindle, okay, or the collet holder, and it will press this so that the workpiece is clamped. So, this is very similar to the clutch pencil. You must be having that mechanical pencil, okay, which is a clutch pencil, and you move that head, and the lid or the pencil lid will come out from this collet. So, that is also collet, and this principle is the same as in here, that is a collet chuck. This is called the face plate. This is face plate attached to the spindle, all right, and this is the work part which is turned in the face plate. So, these are also the clamps which are supporting this. So, this is a special kind of a fixture which is called the face plate. Okay. Now, as I said about the boring, I will go quickly through this, all right, that the difference between the boring and turning is that boring is performed on the inside diameter of an existing hole. The hole already exists and the boring is performed so that the internal hole is enlarged. Okay. Turning is performed on the outside diameter. This is a turning and inside this is the boring tool. So, the boring is made to enlarge that. In effect, boring is an internal turning operation therefore, all right. Boring machines, horizontal or vertical, refers to the orientation of the axis of rotation of the machine spindle. If the machine spindle rotates horizontally, it is an horizontal boring machine, or otherwise it is vertical boring machine. This is a boring machine with the base, work table, work part clamped in here. This is the side tool where the turning process can be made, and this is the tool head where you have a cross rail in which this tool heads can be moved with the tool which are the boring tool which will make the internal hole enlarged. Okay. Shaping and planing, here you can see both use a single point cutting tool moved linearly relative to the workpiece. The shaping operation will show you in the lab also in more details. This is the shaping where the tool reciprocates, and with each reciprocation, that is going forward and going back, I have already told you that earlier, once the feed is given to the workpiece. And here it is opposite in case of planing, when the workpiece reciprocates and the tool is given the feed. You can see here, this is the feed motion given to the intermittent motion given to the tool, and here the feed motion is given to the workpiece, which is also intermittent because in one stroke, and stroke is going forward and coming back, this is one stroke. During one stroke, the feed motion is given along the perpendicular to the motion of the tool direction. Same in here, the feed is given perpendicular to the direction of the workpiece, because here the workpiece reciprocates, here the tool reciprocates. A straight flat surface is created in both operations. This is the new workpiece, new work surface, all right. Interrupted cutting, because this one stroke, after the one stroke it will move and then again cut. Subjects tool to impact loading when entering the workpiece, because each time it is entering the workpiece, okay, in case of shaping or in case of planing, there is an impact loading, and therefore, here what happens is the tool has to be stronger, and any brittle tool that is used here, brittle material that is used, that may actually not withstand this kind of a impact loading. Okay. Low cutting speeds due to start and stop motion. Cutting speed normally used is lower. Shaping and planing machines are like this. This is the shaping machine where the tool reciprocates, and this is the planing machine where the workpiece is longer than in case of shaping machine and the workpiece reciprocates. This is the base, all right. This is the work table on which the workpiece is mounted. This is the cross slide, cross rail, and this is the tool head. Similarly, here also this is the tool head, and this ram reciprocates with the tool, and the tool when it is going back, it will actually not remove the material. So, therefore, going back is at a higher speed, I mentioned it earlier. Okay. And cross rail is used to give the feed to the workpiece after each stroke of the tool. Components of a shaper and planer, I mean, you can make this kind of a surface. These are the components that can be fabricated in shaping and planing. So, these are the dovetails, internal dovetails that I told you that can be machined by a shaping machine easily. These machines are, these kind of slots are used in the milling machine table. Okay. Here for clamping the tooling, the fixture or the workpiece on the table of the machine tool, that is the milling machine. This kind of a V shape can also be cut within this inclined surface can be machined using the shaping or the planing operation. Drilling, here is the here are the details of a drill. Okay. So, starting from the shank, this is the shank where the drill is held in the drill chuck. So, this is the drill axis and this surface is the Morse taper surface. Okay. This has a taper and this taper is of particular type, and this surface is called this taper is called the Morse taper. This is the tang, and this tang is for removing the drill from the drill chuck. Okay. How to remove that we will show you in the lab further. So, here we have the flute, this is a spiral, and this goes all along the body of the drill, that is, and through this the chips can be removed, chips are removed, and also through this the cutting fluid can be actually passed to the zone, machining zone. Here if you understand that when the drilling is made, it is enclosed, okay, whereas in case of turning the chips are coming out easily because it is in the open, all right. But in case of drilling, the drill goes inside the workpiece, and as the drill is made, I mean drilling as the hole is made, the drill penetrates to a certain depth, then it is enclosed. So, it is very difficult for the chip to come out. Therefore, this kind of a flute is given so that the chip can come out through this flute. There is an helix angle here. This angle with respect to the axis of the drill is called the helix angle. This is the body of the drill. Okay. This is the lead of helix, and this is the body clearance. Body clearance is that when the diameter is different from here to here, all right, a little bit, so that the drill can be guided and drill can be penetrated easily to the workpiece. Okay. And here at the geometrical parameters, this is the, if you look at the drill from this side, this will be visible. This is the drill, again the same thing here, and this angle is the point angle. This is the point angle, like in case of the tool, turning point tool, we have shown you that that is the cutting angle. So, this is equivalent to the point angle here, all right. This is the lip, this is the lip, one lip here and one lip here. From here to here, this is called the distance is called the point, and therefore, this is called the point angle. Okay. This is the point angle. Lip length is here, this is the tool diameter from here to here, and this portion is called the land. This is the web or the core thickness, all right. Body diameter or the body clearance is here, and in the other view, here you can see that this is the chisel edge. Chisel edge is here actually. So, this is the nominal relief angle in the lip and in the face, which is the rake face. Here actually the through this and the flute the chip flows. So, therefore, you can show the rake angle here, and the rake angle will show the rake angle in the drill and drill. I have already shown it to you earlier, if you remember, that if you take a section which is perpendicular to this during the cutting process, then the rake angle and the flank angle can be visible along with the chip removal process. Okay. Here is how the drilling is made. So, when the drill is made throughout the workpiece thickness, then it is called the through drilling. Okay. Here is the point angle, this is the diameter of the drill, and if it is drilled up to a certain depth, this is the hole depth, this is called the blind hole. That means, it does not go all through the width of the workpiece. Okay. Now, here one thing that you notice, that any drilled hole, suppose this is the hole which has been already drilled, it will always have an impression of the drill end, obviously, all right. Although this is not required, suppose you drill the hole, okay, tap the drilled hole, make an internal thread, and then you pass a bolt through this. So, bolt will be up to this, and this much is not required, but you cannot help because this is the impression of the drill which will remain here. But in case of through hole, of course, it will not come because it goes out. Here is what I was telling you about the reaming. So, the reaming process is done after the hole is drilled. So, to increase the surface finish of the hole, because after the drilling, drill always will have the vibration, drilling machine will be having the vibration, and normally the drilling operation is the rough operation, because the entire material is to be removed, okay, and there was no hole, the entire hole is made. But in case of reaming, the hole is already there, and since after the drilling the hole diameter is not perfect, not to the desired diameter, and the surface finish is not according to the drawing. So, the reaming is done, so that a very small layer of material is removed, thin layer of material is removed, and material removal is not the basic purpose of the reaming, but basically it is the increase in the surface finish that is required. And therefore, when the reaming is reamer, this is called the reamer. So, when the reamer is selected, reamers always will have the even number of teeth, okay, even number of teeth, these are the teeth. This is because you have to get the diameter of the reamer properly measured, and if it is not even number, in that case the vernier caliper may not sit well, I mean, to find out the exact diameter, because that is measured so that the exact diameter of the hole can be obtained. This operation is called the tapping operation to make the thread, internal thread, all right. And here you can see that this is given as the, I mean, this process is called the counter boring. Counter boring is when we have the two holes of, I mean, internal hole with two different diameters. See, this hole is made, and after that what you will actually have is the hole here, it is a bigger one, and this is the smaller one, all right. So, this is the workpiece, and this is the hole that is made, this is called the counter boring. So, the process is called the counter boring. Now, in case of tapping, you can see that here the diameter of the tap is increasingly more, okay, is increasingly more, because this part is actually making the rough operation, and the subsequent teeth up the tap is making the finish operation. So, finally, what you are getting is the drilled hole, which is the maximum diameter, which is tapped hole, which is of the maximum diameter. So, the drill, that is the tap or the thread diameter, that thread diameter will be according to the maximum diameter of the tap that we have, and the rest of it, that this one is for guiding purposes. Okay. Now, here this is the tool that you can see. This tool is a unique tool, because it will have actually it can have two drills, one drill which will have of this diameter, and one drill which may have of the bigger diameter. So, at a time you can have actually such a drill, such a hole drilled with the two different diameters, one is bigger, one is smaller. This is made just to make the special bolt, to put a special bolt where your bolt head will be sitting inside, and it will not be protruding out of this surface. Okay. So, the rest of the things we will be discussing in the discussion. Thank you for your attention.